offer or propose maybe to leave these 3 problems in chapter 8 in the homework. Okay. And have it due, let's say Friday this week. But if you've done it by Wednesday, that's fine. But whatever that is. 5th. 7th. Okay. Let's see, the final exam. I'll post it on the web tonight, and I'll email you. So it will be due on Wednesday, May 12th. Let's say 5 p.m. Originally the in-class was supposed to be on Monday, a week from today. But being a take-home, I said, just you can have 2 more days. So let's see, the final exam. So this would be posted later tonight. And I'll email everybody. So just try to have a look at it before Wednesday, so we can, if there are any questions, we can discuss them on Wednesday. Also, I'll have some extra office hours. So let's say I have office hours. So this week will be on Tuesday tomorrow from 1:30 to 3. And the usual Wednesday, 10 to 11, but it's not a very popular time. I'll also be here on Friday if you're between, I guess, 10 and 12. So if you have questions, feel free to stop by. Let's see, I think that's all I had for the announcements. I handed in the solutions to the last homework, so I'll post solutions to the homework number 10 on Friday. So, okay, so I want to make the due Friday by noon. Okay, so I can post solutions. And let's see, anything else? I was sad to see that the oil spill is actually now, it's gotten such a huge issue, right? But it's because it keeps spilling, right? It keeps coming. And for those of us that had a good time in New Orleans for some time, you can appreciate, how bad this is. Okay, so let's see. So the plan for basically today and Wednesday is to talk a little bit about Markov chains. Unless there are any. And of course, yes.
Never mind. You'll have the solutions posted, and so how well we did or not did on our own homework, I'll do that input. If we need any ideas from our homework for the final exam, we can look at the solutions that are posted.
Yeah, and it's a good idea to make a copy of your own homework when you submit it. And I'll try to grade it by next week, by Monday, say, if you're. Sorry?
Next Monday is their class.
No, there's no class. They've changed the policy. Yeah.
Are finals cumulative, right? Or is it just on the most recent set?
The final will be on chapter 6, 7, and 8. So just on the kind of chaotic behavior and probabilistic, yeah. No, because I've made myself an image of what that causes. Okay. So let's just talk about. We have limited time, so I don't know how much we'll be able to do on Markov chains, but some of you that already took or are taking the stochastic modeling class have probably seen this extensively. So the point here is that I would like to talk about some processes that are random and they have only a discrete number of states. So it is kind of limiting to only certain models. I mean, you can only use this for certain situations, but it's kind of a start of the more the broad topic of stochastic models. So basically, in the physical models, that the underlying physical model system, is that takes only finite number of states and that can transition between states with a certain probability, with some probability. These usually can be modeled with so-called Markov chains, or a Markov chain. And what's important to understand is that transitions between states can only take place at like finite intervals of time. So it's a discrete. So this is a discrete model, stochastic model. The transitions take place at regular, if you want, intervals of time, every second, every hour, every day, or doesn't even have to be regular, but it's just a prescribed time. So it's not a continuous dependence of the state. Okay? And let's call, so system schematically, if, for instance, if this physical state takes the physical system can take one of three states. So every moment of time you have the state 1 characterizing the system, or state 2 or state 3 characterizing the system, and with possibility of moving from at regular, at intervals, distinct intervals of time, from like state 1 to state 2 with a certain probability. and we're going to introduce this notation of Pij to be the probability of the system in state I to transition or jump to state J. Okay, and you have also a certain probability of the system from state 2 to move to state 3 and so forth, right? And of course you could have B31. You could have that the system that stays, is in state 1 stays in state 1, and that would be P11, P22, P23. Now, oftentimes, if any of this probability is 0, maybe you just don't draw that that arrow or that edge, right? Also, it's possible that the system in state 2 would move back to state 1 and so forth, right? State 1 to state 3. So this would be sort of this would be a complete graph. But notice that, keep in mind that some of these probabilities may be 0. Okay? And there is an example we're going to talk about that has probability 0 and some of them. So certainly these numbers are between 0 and 1 as being probabilities. And there's another very important property of these. And that is, if you're in any of the states, the next iteration of the system, so the next time you have to go somewhere. Either you have to also be in another state. So if you're in state 1 with 100% probability, so it's certain that you're going to either be in state 1, 2, or 3 in the next time interval. And that amounts to saying that the sum of the probabilities, let's see, if you state I, and you're summing up over J, so Pij, again, if you have 3 states, it's going to be for each I from 1 to 3, but for each state, you have the sum of Pij run over J to be 1. Okay? Okay, so this leads to keep this kind of self-contained, it's easy to introduce or to keep this numbers in a matrix. So transition matrix, P, capital P, stands for P11, P12, P13, in this case with 3, P21, P22, P23, P31, P32, P33, and what's important about this matrix is that the row sums, or the sums along each row, are all equal to 1. And of course they're all positive, between 0 and 1. It could be, some could be 0 or 1, or sums are all positive, equal to 1. Okay? So this defines P is called such a P. So such a matrix that has these properties is called, okay, P is called stochastic matrix. if all entries are positive and the rows or sum is equal to 1. Okay? Or non-negative. Okay, so here's the example that to start with. So the example is this inventory problem. That's number 8.1. Okay, and it has to do with, I guess, inventory of aquariums, or aquaria. I don't know what's the plural here, but what happens is at the end of each week there is an inventory that's being done, and depending on how many were sold during that week, certain strategy for ordering for the next week are used. So the policies that if there is nothing left, so if everything was sold at the end of the week, then there's going to be 3 aquariums. So there are going to be 3 aquariums ordered, right, for the next week. If there is any, if there is at least 1 aquarium in stock, then there is nothing ordered, right? The policy is based on the observation that the store only sells an average of 1 aquarium per week. Okay, so it's saying that even if there is only 1 in store at the end of the week, it's likely that no more than 1 on average is going to be sold, so they're not going to order. Okay, so why is this system sort of modeled using the Markov chain, or I guess in its simplest the simplest approach is to think about this number of aquarium at the end of the week. Okay, so there could be, or at the beginning of each week. Okay, so at the beginning of each week you could have 1, 2, or 3. Can you have 0? Well, if you had 0 at the end of the week, the next you order 3, right? So you really never have 0. That's why 0 is not a state. So this is.
But I thought 0 was a possible state because they're saying that the question says adequate policy regarding potential lost sales because the customer requesting one when they're out of stock.
Okay, but that's the question. Okay, so
if they're out of stock, then you have a possible state of 0.
Okay, but let me clarify. So these represent the state, the inventory at the beginning of each week. Okay, so you cannot have 0 because you've ordered 3. If you had 0, okay, then you've ordered 3. So you start the week always with something. The question asks is, what if during that next week the demand is actually higher than what your inventory is? What's the probability of that happening?
So we're assuming that the time interval between order and receiving.
Yeah.
We're ignoring that.
No, yeah, we're ignoring everything. Yeah.
We're just assuming that that's just okay.
Simplest.
Simplest
Okay.
possible. As soon as we order, we have stock.
Yeah.
Okay.
It's next door. Okay, garage sale, whatever. Okay, so all right, so there's going to be probabilities of something happening. For instance, what's the probability that you start 1 week with inventory of 1, right? And you move the following week with inventory of 2. I'm sorry, this is okay. It's a little bit. I mean, to get to the probability to the actual probability, it's a little bit. We need to go through another step. So that is the following. So let's call xn to be the number of aquaria or aquariums at the beginning of a week n, okay, and let's call dn to be the demand for aquariums during that week, during weekend. Okay, so trying to figure out what's the probability of moving from one state to another. Okay. All right, so we have the following. What's the probability that you are in state 1 and you are in the next week you're going to be in state 1? Okay? Well, that probability is obviously going to be equal to the probability that the demand during that week is 0. Okay? So we'll talk a little bit more about this, what's called conditional probability, but clearly, you're going to start with 1 aquarium, and the following week you're going to have 1 aquarium if there is nothing sold, right? So the first thing to decide is what should be the probability that the demand is 0, or what is the probability that the demand is any given number? Okay. Well, so the question is that this random variable, which is the demand for aquarium, is a discrete random variable, right? So this is a discrete random variable and can take values 0, 1, 2, right? It could be, the demand could be huge, right? So in theory, it could be any integer, right? So the question is, what is the probability density distribution? So the probability distribution is assumed to be exponential, or excuse me, Poisson. because it's discrete, and it models this kind of time over, number of arrivals, if you want, during any given week. Okay, so it's going to be a very low probability that this D is going to be high. There's going to be a reasonably high probability that this D is going to be small. So this is going to be our assumption. Assumption is that the probability that dn takes value, any value k, is going to be e to the minus lambda, lambda to the k over k factorial. Okay? Now the question is, this is Poisson, what is the rate? So recall the expected value of the Poisson distribution is actually lambda, right? So if in our case we're talking about 1, what was it, 1? Right? Observation that the store only sells an average of 1 aquarium per week. Right? So so the assumption is that this is equal to 1, in which case the probability that dn is any k should be considered to be e to the minus 1 over k factorial, right? So let's just write this down. So what is the probability that the demand during weekend is going to be 0? And it's e to the minus 1, right? 1 over e, whatever that is. What is the probability that there will be 1 so same, right? E to the minus 1. Probably there's going to be demand of 2. This should start to drop, right? E to the minus 1 over 2. By the way, these numbers are 0.368, I believe. 0.368. Well, this is half of it, right? So 0.184, right? And so forth. What's the probability that the demand is going to be 3? Well, right? So it's going to drop. Is this a fair assumption? Well, it depends on the market, right? I guess conditions or something, but that is an assumption, to a working assumption. Okay, so these probabilities will basically affect this transition probability. So this P11, now we know what the P11 is, right? We'd have to compute. Okay, so now let's go back to the transition probability. So P11 is going to be n plus 1 is 1, given that xn is 1. So this is going to be probability that dn is 0. So this is 0.368. Let's compute the next one, which is, I guess, well, the easy ones are the ones where n plus 1 is 2, given that xn is 2. This is the same. So the event basically can be characterized by there's no demand during that week, right? So that is going to be the same, 0.368. But unfortunately, P33 is not going to be that easy. So the P33 is the probability that during week 3 there are 3. The beginning of week 3, weekend plus 1, there are 3, given that at x n equals 3. So here there are two possibilities. There are two mutually exclusive or disjoint events, right? So it's the probability that there is no, so there were 3 and there's no sale. So that is one possibility, that there is no demand, right? But it's also the probability that there is, everything was sold, right? All those 3 were sold during that week, and then you have replenished, right? So there's a probability that.
Isn't the same true for 2 and 2?
No, because.
You have demand of 2.
But then you replenish to 3. So you can never start the week with. If you sold everything during the previous week, you always replenish with 3. Okay. So this one. Okay. So now the question is, how do you compute this? Well, it's obviously going to be a series. Okay. So you can do it as a series, or it's possible to think about the complementary event. That is, so it's going to be 1 minus the probability that neither of these happens, right? Which means is the probability that dn is 1 and the probability that dn is 2. Okay? And now this is you can compute this. So it's going to be 0.368 minus, and the other one was half, right? 1.84, and I think this ends up being 0.448. Of course, it's the first 3 decimals. Okay. All right. So again, I'm going to leave this because it wasn't clear in the beginning how to compute this, but now we can start to make ourselves an image of this Markov chain. So it basically says P11, P22, and P33. Okay? But now, of course, the other ones need to be computed. So for instance, what's the probability that you start with 1 and the next week you have 2? 0. Right? It's impossible to end up with 2 during any given week unless you started with 2 or the previous week. Yeah.
Could you say a few words on how you got the complement above?
You mean here, this one?
Yeah.
Well, remember the
What is the process you think?
well, you have a random variable that takes discrete amount of so it has a probability distribution, right? So it has a probability that it's 0, that it's 1, that it's, and so forth, right? So basically each of this bin is a probability of an event, right? And these events, the union of those events are mutually exclusive, and they add up to a certain event. Because something has to be, right? The D has to be something. Yep. At each week, D has to be equal to something. So all we do here is say if the sum of these things equals 1, well, and we're only looking at basically at the one which is 0. So I'm going to use the red to indicate. So this is 0, 1, 2. 0 is here, right? So it says the probability that of the event that this happens, right? And this happens. is 1 minus the sum of those two probabilities. That's all. So the sum of everything is 1, right? That's and these are mutually exclusive events. Right?
So the probability that dn is greater than equal to 3 is 1 minus 0.368 minus 0.368 minus 0.184, and you're just canceling those 0.368s there.
Yeah.
Or one of them.
Right.
Right?
Well, so again, this is just to avoid computing a series, right? That series that will be a series from 3 to infinity of those exponentials, right? Okay. All right. So there's nothing between 1 and 2. So you can draw and draw 0, or you just avoid drawing that. Let's see something that actually is not 0. So from 1 to 3. So what's the probability that you start with xn plus 1 is 3 when you started with xn equals 1? How can you write that event in terms of d? Greater than or equal than 1. Again, demand could be very high, right? You can only sell what you have, but the demand could be very high with low probability, but it could be very high. Okay, so this is again the same thing. This is 1 minus what probability of what event? The dn is 0, right? So this is 1 minus 0.368. So this is whatever 0.632. Okay, so that's a pretty high probability that from 1 you move to 3. Right? And then you can keep doing this. So let me just leave this and write what the matrix is. So that's the nice thing about putting everything in a matrix. You can see everything at once without having to draw all those arrows. So this is 0.368, 0, 0.632. Second row is, we haven't computed P21, but it ends up being when the demand is 1, and that's 0.638, 368. We haven't really computed the probability that you start with 2, you end up with 3, but again, that translates into an event of related to the random variable d. And the last row is this one. Okay? So this is a 3x3 stochastic matrix. Okay? And now the question is, what do you do with this? So what is this matrix used for, or this probability transition probabilities used for? So I guess I should talk a little bit about the conditional probabilities. So let me make a parenthesis here, and so we don't necessarily see this ugly numbers here. So let me just simplify. So consider a simpler 3-state Markov chain. As follows. So same 3 states, so 0, 1, 2, and 3. Okay, and let's imagine that we have the random variable that has basically just is the state at time n, and it has the following distribution. So it is state 1 with a certain probability, and I'm going to take just different numbers. Let's say it's equally likely that the state is 1, 2, or 3. So the probability that x1 is 1 is 1/3, that x1 is 2 is 1/3, that x1 is 3 is 1/3. Okay, and consider the transition matrix. To be the following. So let me write this down. 1/3, 1/3, 1/3, 7/10, 3/10, 0, 0, 1, 0. Okay. I guess I should have said what x0 is. So x0, I want x0 to be 1. So I want to start at 1, and I want to move in the next state, so state at time 1, with equal probability at being 1/3. Back 1/3 probability is at back at 1, 1/3 probability is at 2, 1/3 probability is 1/3, right? So the question is, what will x2 be? So what is the state at second time going to be? Okay. Well, so here we need to, obviously it's going to be 1, 2, or 3 with probability that x2 is 1, which we need to compute with x is going to be 2 with the probability that we need to compute, and it's going to be 3 with the probability that we need to compute. Okay, so let's take it one at a time. So what's the probability that the second state, or the state of the system after second iteration is actually 1? Let's see, okay, so I gave the transition metrics here, but it's not that clear, because you can actually be in, let's see, state, the second time you're in state 1, but you could be staying in state 1, right, and just between 1 and 2 you stay in state 1, right? Or you could be going to state 2 and then coming back to state 1. What is that probability? That probability is 7/10. Or you could be going to state 3 and then come back to state 1 with well, that's actually 0 probability, right? So I think this is accurate diagram. No, there's a probability that if you're in state 2, you come back to state 2.
Says that state 3 to 1 is probability 1.
No, if state 3 to 1 is 0. Just the way I wrote here. Oh, 1, 0, 0. Okay, so let's So then that changes what? Three 2 is 0, right? So 3 1 is 1. Okay? Right? So if you're in state 3 with well, probably 1, you go back to 1, right? So you can actually x2, so x2 is a state at time 2. It could be 1 as follows. So here are all the possibilities. There's a probability that x2 is 1 given that x1 was 1, right? So let's see, this is times the probability that x1 was 1 plus, so I'll say in a second, this conditional probability is the probability that x2 is 1, that x1 is 2, times the probability that x1 is 2, plus the probability that x2 is 1, given that x1 was 3, times the probability that x1 was 3. Okay, so here we use the following notation. So P of A and B, A condition B, or A given B, is a conditional probability of the event A given B, and in discrete probability there is a way to define this, actually, I think in general. By definition, this conditional probability is the probability that both events A and B happen when the sample space is reduced or is restricted to B, right? So here's the picture in general. If I have, this is my sample space, and I don't know, I think we use it as for discrete, right? If this is a sample space, and this is the event B, okay? And I have some event A, let's say it kind of overlaps, partially overlaps with this, right? Then what are we doing? We're saying that the new sample space is just B, because given that B happens, what is the probability that A will happen, right? So at least when you do counting, when it's equally likely outcomes, you can see that the probability that A will happen, knowing that B already happened, or that B happens, is the number of outcomes in the intersection divided by the favorable possible outcomes, right? So it's the ratio between P of A intersect B and B. Okay? So now why do we actually do that product that I wrote there? Well, so imagine that I have, for instance, that the event A is the event that x2 is 1. Okay? And the event B1 is the event that x1 was 1. B2 is the event that x1 was 2 at the previous, at the time 1. And B3 is the event x1 was 3. So I have these three events. By the way, they are mutually exclusive. What does that mean? It means their union is actually the whole space, the whole sample space, and they don't intersect each other, right? Yeah. So I have three events. So now, at time 1. Now at time 2, I'm looking at the event that x2 is 1. So what can I write? I can write that the probability that if the event A, actually just the event A, I can split the event A into the following. I can split the event A into 3 sub-events. I mean, if I had 3 colors, right? So this is B1. This is B2. Or B2 here and B3 here, right? And my event A is somewhere in here, right? So there's going to be is the disjoint union of three sub-events, if you want, event A, right? Okay, being disjointed means that the probability of the event A is the sum of the probabilities of the sub-events. And now all it's left to do is to say, can you write this in terms of conditional probabilities? Well, so if the conditional probability is the ratio between the probability of the intersection and the probability of B1, for instance, then this intersection is going to be probability of A given B1 times the probability of B1, right? Plus and so forth, right? Probability that A given B2 times the probability of B2 plus probability that A given B3 times probability of B3. Okay? So that's exactly what. It's just this is just a set theoretical, if you want, computation. Except here I use this concept of conditional probability. Okay, so that's actually what we wrote here. So it's the probability that the event A is split into 3 probabilities. And we use conditional probability because these are just those transition probabilities, right? So let's just compute again that P of x2 is 1. So what's the probability that x2 is 1 given x1 is 1? That's P11, right? Times the probability that x1 was 1. That was conveniently chosen to be 1/3. Okay? But then is the probability that P2 is 1 given that P1 is 2. So that's P21, probability that x1 is 2, and P31, probability that x1 is 3. So what was P11? 1/3. What is the probability that x1 was 1? That was 1/3, right? P21 was 7/10, and then 1/3, plus P31 was 1, and this was 1/3. Okay? So what is that? $17 over, is it 90? No. 47 over 90. No, that's not even true. Uh, 10, 21, and 30, 61. Yep. Okay? So that's how you, then what's the probability that x2 is 2? What's going to be P11, probability that, P12, probability that x1 is 1, plus P22, probability that x1 is 2, and P23, no, P32, probability that x1 is 3. Okay? So it seems like something that becomes tedious, but fortunately there is going to be a pattern here, which very soon we'll write down. But so let me just do this one. So 1/3 and 1/3 plus 3/10 and 1/3 plus 0 times 1/3, right? Okay, so this is 19 over 90, right? One-ninth and 1/10, right? Okay. And finally, P, probability that x2 is 3 is, so you see why it's easier to work with this number than with those coming from the inventory problem. P31 and so forth, right? And since we look at the metrics, we can tell this is 1 times 1/3 plus 0 times 1/3 plus 0 times 1/3. So this is 1/3, or if we were to put it over 90, no. P3 was 1, right? P31 was 1. Does it look like 30 over 90? So does it add up to, it should add up to 100, right? 100%. Yeah, why is it? It should be 1. Okay, we can figure this out, right? It's not 61 here, but it's so it's 1/9. I think it should be 41, no?
Should your second set of equations should be P21 rather than P12?
No.
No.
No, because this is the probability that x2 is 2 given x1 is 1. So it's moving from 1 to 2.
We were right, 61 over 90.
So why doesn't it add up to? So why is this? Okay, so looks like they say this is 1/9. Why is this 1/9?
So P31 should be P1.
Yeah. Okay, thank you. That was the problem. And that's 1/3. Thank you. Okay, so this is 10/90, so 1/9, right? All right. Okay, so all this computation was to just figure out what is the probability distribution of this x2 random variable, which is, this is with so it's equal to 1 with some probability, equals to 2, equals to 3 with some probability, right? With probability 61/90, with probability, what was it? 19/90, and this is with probability 10/90, right? Okay, which should add up to 1. So then you go to x3, right? Okay, but at this point you don't want to do this tedious computation again. But instead, what you want to do is the following. So you notice the following thing. So you notice that the probability that xn plus 1 is some value j, well, j from 1 to 3, is actually the summation over all I of pij times the probability that xn was I. Okay? Which would be what? P1j, probability that xn is 1, plus P2j, probability that xn is 2, plus P3j times the probability that xn is 3. Okay? This is in the case of 3 states. But if you have n state, 5 states, it would be summation over all 5 states and so forth, right? So here's kind of the magic thing that happens, is denoting pi n of I to be the probability that xn is I. What you're getting is a row vector which is pi n of 1, I don't know, let's say pi n of 2, pi n of 3, then you can write this as a matrix multiplication. Okay? You can simply write that as being the row of pi n, right? Multiplied by the columns of p. Okay? So then we can write the following, that pi n plus 1 is simply pi n multiplied by p. Okay? So specifically, if I have 3 it's a 1 by 3 row, so this is pi n plus 1 state. This is going to be the row at time n, so pi n, and then I have multiplied by these columns, right? Yeah, so we were looking at the wrong. So you should be multiplying the values, the current values, the probabilities that the xn is in any of the states, by the columns of this matrix. So that's why when we looked at the matrix above, somewhere here, it was always multiplying by these columns, right? So now, if you have to do x3, then you would just take the probability distribution of this x2, put it in a row, and multiply by p, and you're going to get the new row that's going to be the probability distribution of x3, and so forth. So in general, you're going to get the probability distribution of. So this is going to be the probability distribution. So pi n is going to be the probability distribution vector, if you want, of xn. Okay? Meaning that xn is going to be 1 with probability pi n of 1, 2 with probability pi n of 2, and so forth. Okay. So finally, we can go back. So we can go back and talk about what happens with that with our original inventory problem. But so let me introduce the last thing, which is called the limiting probability. Okay. So the limiting probability so if we start, let's say start with pi 0, then compute pi 1, which is pi 0 times p, pi 2, which is pi 1 times p, right? And this is pi 0 times p, or p squared. So in general, it's going to be pi n is going to be pi 0 times p to the n. So it's going to be a sequence of distribution vectors, right? So if pi n converges to some vector pi star, then pi star is called a limiting probability. Or steady, actually, so it's a limiting probability, for the Markov chain, or for the Markov chain. And the most important thing that's going to be satisfied by pi star is that pi star, so remember pi n plus 1 is pi n times p, and if pi n goes to pi star, pi n plus 1 also goes to pi star. So pi star satisfies this relation, that pi star multiplied by p to the left, I mean pi star multiplied to the left of p, is the same as pi star, right? And that's means that pi star is a steady state distribution for the Markov chain. Turns out that actually you can compute this fairly easy, because all this pi star is an eigenvector corresponding to the eigenvalue 1 for p, or p transpose, right? So pi star is a left eigenvector for p, which corresponding to eigenvalue 1, or if you don't like the word left eigenvector, then, or pi star transpose is a right eigenvector or eigenvector for P transposed. Okay. So in MATLAB, you can actually, when you put in this matrix and you look for the eigenvalues and eigenvectors, well, if P is a stochastic matrix, you're going to always get an eigenvalue of 1, and the eigenvector that corresponds to the eigenvalue is going to be the steady state distribution. Last word is, how does this reflect back to the inventory problem? So if you do that, we computed the matrix. We computed that metric. So back to inventory problem. Pi star turns out to be the following: 0.285, 0.263, and 0.452. Okay, so I'll talk about more about how to actually compute this in practice. But with MATLAB, we can find these numbers by just putting that matrix P, capital P, and the conclusion of this model was to figure out the probability that the demand exceeds the inventory, right? So it was the question of what is the probability that in week N, for instance, the demand exceeds inventory. So here's what you do is, again, you split into the case when the conditional probability that demand exceeds inventory when inventory is 1 times the probability that the inventory is 1, and so forth, right? Probability that dn is greater than xn when xn is 2. We did in a second. Xn is 2 and 3, right? And now the question is, what numbers one needs to put in here? Well, what's the probability that the demand exceeds xn when xn is 1? Well, that's the probability that dn is greater than 1, right? And that we know how to compute. It's basically 1 minus 0.0368 minus 0.368. But the question is, what is this one? And that's where one uses the limiting probability for those values. The probability that xn is 1 is 0.285, right? This is 0.263, and this is 0.452. Okay. So when you plug in these numbers, and you have to trust me on this or the book, you get something like 0.105. So this is 10%. So 10% chance that you, following that policy, you're going to actually have the demand exceed the inventory. Okay. So on Wednesday, I'm going to show you kind of, I guess, on using MATLAB, how you can actually generate this limiting probabilities, either through the discrete dynamical system or through eigenvalues. Yep.
Just go back up when you're talking about the pi star is the left eigenvector for P. What's the word right after P?
Corresponding to eigenvalue 1. Okay, so we'll talk more about this on Wednesday. Thank you.